Okay, so this slide, the table on the left-hand side shows some historical blackouts starting from the very first one, which is the first one well known by the over the world, back to 1965. That's the first very large power blackout, and that also make people realize the power system blackout has to be prevented at the system level. So you cannot eliminate such a power outage by only putting protection on the grid. You have to study the entire system as a single system in terms of the reliability, security, stability. So there are a number of things which make the power industry change. Number one is what you have known. The NERC is actually was formed a couple of years after 1965 blackout. If you remember we have previous slides talking about the history of NERC. So NERC was formed back to 1968. So that's about 3 years after the first blackout. Another thing is the Electric Power Research Institute have been working with was formed also around the same time. So there are a lot more activities to study the power system at the system or the grid level. Okay, so and they also show some other blackout. And the next one, which is also in the northeastern area, actually in the New York City area, is 1977. And another two, which happened in the both in the Western Connection in the same year. So one was in July, and the second one was in August. And the two blackouts were caused by totally different reasons, in about the same area, but by different reasons. So we'll go back to those each individual blackout event, and when we talk about the specific stability issue. So the one in July was caused by voltage stability. So we have one session about voltage stability. We'll use that one as an example to explain what happened. And the second one was caused by oscillation. The oscillation will broke the system into 5 islands. And then some islands have more load, some island has more generation, and then blackout happened. Okay. And there's also some other blackout in not in the US, like in Brazil, Italy, Europe, and there's one recent one, 2019. So in South America. The most recent blackout in North America was in 2011. 2011 in the Southwest blackout. So this chart does indicate the impact of each blackout is depending on how quickly you can bring the system back. Okay, so that depends on a number of factors. First of all, so if a blackout is limited in a very small area, you can definitely recover it easily, right? If it's spread out for the entire system or entire interconnection, that takes much longer to recover. Second, even the blackout cover pretty large area, and if the operators were trained very well to bring the system back, they can take actions, they can avoid miss operations, they can bring the system back. There could be some mistake that happened during the system restoration. For instance, I participated in one power system restoration drill. Drill means they just, as I mentioned in the last lecture, so each control room has typically at least three rotations. So each rotation team will work for 8 hours, right? The other 2 teams will wait, they will take a rest, and they will come back. But when one team is working and the other team can do like training or drill, or if they're not sleeping. So there's one drill was organized by the Western Connection, focusing on the California area. I participated in that drill. So that drill lasts for the whole day. Okay, so in the early morning, so the California ISO, the operator, and all the plant engineer operator from a different utility company, they all came to the same hotel. Okay, the hotel have very large conference rooms, so once they enter, they cannot leave for the whole day until they bring the system back. So they use a simulator simulating the entire Wi-Fi connection. So what if this happened and trigger maybe the line from a Pacific Gas and Electric PG&E transmission outage and cause California entire system oscillating and then trigger some power plant belonging to another utility company. So they try to work together in the same large conference hall. And the setup is each company will can only sit on the table, and they can communicate with the neighboring table, which is from another company, but only by the legal way, right? So usually, in reality, they will make a phone call to call the other desks to collect the information if they don't have that data. So they have to follow specific protocol to communicate between different table. What was interesting is it take a whole day from the early morning until 5 o'clock. They failed to bring the system back. They made a number of mistakes. The system crashed again. So finally, in order to wrap up this training, they have to load another file, which is almost ready, right? They have to practice the last step because there are a number of things they need to do. When the entire system is in black, they need to start the first power plant, or maybe one unit, which is called black star unit. So that black star unit can start up on its own. Usually such unit can be a combustion gas turbine. They can quickly start. And they use this unit to connect a transmission line, but because the line has no load, so the generator only generate a little power. And then along the line, they can maybe pick up some critical load. If there's a hospital, they have some very critical, like airport, they have to bring those load back. So they gradually pick up load and also pick up other generators. So that take many steps. And for a system which is very large, like a Wi-Fi connection, they can be recovered on each individual utility company. So each utility company may have their own black star unit, right? But when each is started, so they can operate as island. So the last step will be resynchronizing all the island together to the original system and recover frequency back to CISC. So they hope they can finish such things in like 1 day or at least in 8 hours. But you can tell there's some black hole. They really take a long time to recover. Okay. So definitely this course, we are not going to discuss how to mitigate or control or restore power blackout, but we want to cover very basic concept about power system reliability. So we want to learn how do we do the reliability study under normal condition, right? To study what contingency may impact the system. We definitely don't want anything here to happen, but we want to learn how the engineer deal with contingencies of the system. Okay, so let's talk about the reliability. So we have to narrow down the definition of reliability under the concept of either the bulk power system or bulk electric system. So BES was defined by NERC. So when starting from this slide, any reliability is regarding the BES. It's not about like a microgrid or some other grid at low voltage. We're talking about some system at about maybe 100 kV or higher. So power systems should be built and operated to achieve a reliable electric power supply at the most economical cost. So this sentence mentioned 2 things. One is reliability, the other is economy. How can you operate system at a minimal cost, but still maintain reliability? But here, what this sentence want to say is reliability is really more important than economic about the power grid. So if the system is reliable, you try to achieve the minimal cost, right, to make it be economical. But if the system is not reliable become the top priority, okay, for the operator to address. So if we want to define what reliability really means, so there are 2 terms, concept related to reliability. So reliability covers both concepts. The first one is called adequacy. So adequacy is from the planning perspective. So it means the ability of the electric system to supply aggregate electric demand and energy requirement of their customers, consumers at all time, taking into account scheduled and reasonably expected unscheduled outage of system elements. So basically it means the system, when it's planned or designed, they need to have enough generation to support the total load. Okay, so like if I'm the plant engineer, I'm the operator of one power grid, I can do like full load forecasting, long-term load forecasting, so to estimate how quickly the load can grow. So this spam phone call every day on the same time. Okay, so I need to estimate my load, the growth of my load, and also make sure my generation capacity is higher and maintain a certain margin, because even the total generation is equal to total load is not enough, because sometimes you need to do some maintenance, like a rolling blackout, or you have to do some maintenance of unit. You need to have backup unit. So usually the peak generation is much higher than the load. So if that's true, and the margin is also enough, I can see I have adequate generation, and my system is reliable from the adequacy perspective. But that's not enough, because the second one is called security. That's from operations perspective. So security concerns the ability of the system to withstand sudden disturbances, such as like a short circuit or loss of system elements. So not only your generation need to be higher than load, and even after any contingency, any disturbance, your generation is still higher than load. So that's considered security, and for any time. Okay, so in the planning stage, at least long-term planning stage, adequacy will be the important theme to study. But in the operation stage, security will be critical. Give you one example on the difference between the adequacy and the security. Let's say you graduate and you get a job offer. Okay, so after you interview, they gave you a big offer. The job offer is like $300,000 per year. Okay, that's written on the offer letter, saying your annual salary will be $300,000 per year. Okay, then you feel that's pretty adequate, right, to cover all my expense, no matter where, as the entry level job. Then you start working at that company, but at the end of the month, you didn't receive the paycheck, and you talk to the HR. HR said, if you read, there's a last sentence on the offer letter saying you're going to receive paycheck every half year. Okay, so then you feel that's a big problem. I have to go through the first half year. Even the total salary is adequate, but it's not secure, because what if something happened? I have to go to the hospital, right? That's a security problem. Okay, definitely if you have like deposit and you have a lot of money, have backups, it can become secure. So secure does need a lot of backup. Okay, not just about the total mass, the total number. So if we talk about the detailed requirements of reliability, so there are some things we have to check. First is the voltage, and second, frequency. So usually voltage at high voltage level, about higher than 100 kV, the voltage variation should be less than typically like 5%. The higher the voltage, the smaller tolerance you can have. Like if you check the voltage at low voltage level, like feeder, like maybe you just put a meter, measure the voltage there, that can vary a lot, but it doesn't, because we have like a power supply to help you to stabilize voltage. So it's not really a big problem. But at a high voltage level, 100 kV, so you really need that voltage to be very close to the nominal value. So 100 should be 100, okay? If it's not 100, temporarily become 95 or 105, that's also okay. But it cannot be like 90 or 50 or 80, right? And the frequency, we are using like 60 Hertz AC power system. So 60 Hertz means usually the frequency cannot vary by half Hertz. When we go to the frequency regulation section, we'll talk in more detail about what range of frequency we can operate the system. Like if the frequency is very close to 60 Hertz, there's no damage to any equipment. But if it's like higher than half Hertz, some equipment will have shorter life. And if the violation become 1 Hertz, temporarily it's okay, but some unit has to be tripped, like not after a long time. So typically the half Hertz divided by 60 Hertz is about like 1%. So like 1% variation for frequency and maybe 2 to 5% variation for voltage, acceptable. Acceptable means not good, but it's okay. It cannot be worse than that. All the synchronous generators need to be connected and running in parallel, which means they have very close frequency. Okay, they are synchronized. Also, there's an integrity, means the entire network is connected. Okay, you cannot break into a hub or maybe several islands. They can temporarily operate in islands mode. When you bring the system back from blackout, you can operate maybe in islands like maybe a couple hours, 10 minutes, but it cannot operate in under normal condition. Okay. So how a reliability standard used in planning? So reliability standard, so here we're talking about standards proved by, actually developed by NERC, but proved by FERC. Okay, so when NERC developed such criteria and finally proved by FERC, and it will become a official standard. So those standards should never be violated when you design the system. There's no way, if you're a member of NERC, you have to follow everything for those standards about designing the system. So for power system at its designing state, it can never violate any reliability standard. What does that mean? It means definitely if you load at this level, your generation should be higher and the margin should be higher than certain value. Okay, and if some generator be mounted, you need to have a typical, you need to have a very detailed procedure talking about how you can mitigate the violation. Okay, everything will meet the standard of NERC. But in reality, if something happens, the standard should not be violated intentionally, which means you try your best to follow the standard. If something really happened, like blackout, if a blackout happens, of course, many area of system will violate the standard, but that cannot be intentional. Okay, you try your best. Definitely, they will after each major outage, utility need to send a report to NERC, and usually after maybe 3 months or half year, they will check all the report to make sure you are not violating any standard. So if you are violating standard, that you will receive penalty. Okay, the penalty will be definitely used back to your company, but to train your engineer regarding standard. But that's fine. That maybe there's also some lawsuit following that. So that is also why if you hear any news saying like we have blackout in Tennessee, and if you talk to TVA, they will never tell you what happened because they have about half year to report back to NERC before they conclude what really happened. They cannot share anything, right? But if you have a like F9 device, like Professor Liu school is maintaining, that one usually can tell what's happened, but that's not the official conclusion. So typically after such large event, the DOE may some officer from DOE may call Professor Liu, say, hey, what happened from your data? And you can provide. So usually you have to know officially what was happening. That's half year later at least. Okay.
Public, what's their evaluation?
I guess the report is public. At least all the final report about the conclusion definitely need to be public. Definitely the information, some information are confidential, like the location, the substation name, and which how the layout, design, the substation. They don't have to disclose that such level of details. But definitely the final report, you can, for the table with a lot of historical blackout, if you search that name, you can find they're all from the report. Yeah. Any other question? Okay. All right, so this table shows all the contingencies you need to study for BES. I just put some lighter with color that indicate their category, roughly what they are about. So if you can see the first column starting with P0. P0 means no contingency. Okay. No contingency is also considered contingency because that falls into the normal condition. But normal condition, the system may have load variation. So which means if you don't lose any element, even the load can vary a lot. You still need to do such study. It will be considered as like a P0 level contingency. Starting from P1, and P1 and P2 will be n minus 1. N means the original number of elements of your system. Minus 1 means you lose a single element. So that's called n minus 1. That's a typical way. If you talk to a power industry about contingency type, they usually just tell you, okay, we need to study n minus 0, n minus 1, and n minus 1 minus 1, and n minus 2. Okay, they may say, we only study n minus 1 minus 1, but not n minus 2, right? So you may wonder what are they different? Because n minus 1 minus 1 means based on n minus 1, you actually take another element. But n minus 2 means you arbitrarily take any two elements, right? Which actually broader than n minus 1 minus 1. Okay, so on the top, the higher the contingency are more commonly seen in real world, but bottom one will be fewer contingencies. Let's see, give you some example. Okay, so for single contingency, it definitely means just loss of one element. But at BES level, one element doesn't mean a single line or single node of your graph, because we're talking about detailed grid model. So if you look into the details, so MS1 means maybe you lose a line section. Line section, if you have a long transmission line but split into multiple sections, each section is protected individually. So that section is considered one element. So this can be different from what you know about like a single contingency. So if you, as PhD student or master student, you can work on research paper. If you study contingency, you can see, okay, I consider contingency, which is loss of single line. Maybe okay for like research. But if you work for power industry, usually if the whole line is one section, that's whole line, but it can have multiple sections. Like bus section fault. Bus section fault means bus is a substation, but if you go to any substation, they have a very complicated like layout map for the entire substation. But in our model, typically we only consider a single node. But if you look inside the node, that itself is also a system. So power transmission substation is also a power system, right? So it's maybe much more complex than any microgrid. So each section need to be protected by protection. So if you lose one section, you're going to lose all the lines connected to that section, but the other lines, even they go through the same substation, but not in this section, they can still operate. Okay. Yeah, so there's many other details. If you can, you download this slide, you can check the detailed contingencies. Basically, in this table, you need to study all contingencies fall into those categories: MS0, MS1, MS2, but there's no MS3. Okay, but if you look into some detail, some contingencies, it doesn't stop you to study MS3. Like for instance, if you lose the entire substation or entire bus, all the line, no matter how many connected, they will be lost, right? So that's already, so the effort to study such contingencies equivalent to study maybe just losing a single line or two line. Okay, so you can study, but randomly pick any three lines or three elements to trip is not required, because that they understand that the effort is a lot. Okay, so this is how it's called somehow like a deregulation, because all the standards are designed by the utility people and also people with system operator. So they cannot create a standard that they will never be able to make it. This table gave you more detailed study on what specific simulation study you need to do for each contingency in the previous table. Like for instance, like they give you more details, like with initial condition, single generator, and there's some maybe short circuit outage, and like three-phase fault on generator and three-phase fault on transmission line. So you need to do such. On the right column, you need to do pretty much time domain simulation to study dynamic. On the left column, it's called steady state. You only need to run power flow. Okay. So you just need to remove that line and solve power flow and to check whether the voltage or the power are violating the limit. But on the right column, you need to do time domain simulation to make sure the system is stable. All generators synchronized and frequency are okay. All right. So this slide just talk about some idea why we need to categorize those contingencies and how to select the most important contingency to study. So we need to, because all the selection of the contingencies is to deal with mitigating the risk of the system. So the risk of a power outage or risk of a blackout can be defined as the product of the probability and the cost. So there are some contingencies, the probability is very high, so it can happen every day. But if it happens, it's not really big deal. It's just typical, very close to normal condition. So which means the probability is high, but the cost is very low. It doesn't impact anyone, right? The cost is zero. Then you don't really need to pay too much attention on such contingency. But there are also some contingency. Once it happens, the entire system is down, and it takes like the whole week to bring the system back. But based on your evaluation, the risk is very low. It only happens maybe 20 years, once every 20 years. Then that's up to you. If you like, you can do such study maybe every 5 years, right? It should be okay. So which means when we select contingency, we need to select the ones with higher risk. Okay. And which means the product of the probability and the cost should be higher than certain value. So then the axis, I call it a consequence, which is the cost. The consequence means the loss of need to bring the system back. So they all fall into the cost. It can be considered as some factors of the cost. And the y is the likelihood, which is probability, how often this event can happen. Okay, so that curve is roughly like a quadratic curve, which will just indicate they have along the curve, they have about the same risk level. So under the curve, which means the risk is lower. Higher the curve means the risk is higher. But if the system is well designed, it should not be much higher than the curve, right? If it's much higher, which means it's a design problem. You didn't design the system well. But if you design the system well, all the contingencies to be studied need to be along this curve. Okay, so for those contingencies on the left, right, which will be MS1, like a single generator outage, single line outage, and the yellow one will be like MS2, loss of 2 elements, and the red one will be an extreme event with loss more than 2 elements. Okay, so we put all the contingency from previous slide into this table. We have a P0 on normal condition, P1 and P2 for single contingency, and P3 to P7 double contingencies. Red one is not here. Red one is extreme event. Extreme events are not required. It's up to you. You don't have to study all the extreme events because they are very rare. But if it happens, it will cause a lot of consequences. So it will not be the matter whether the NERC will give you a penalty. It's really about how you can meet your customer's expectation, right? So if it happens, your customer is very unhappy, so you need to do such study. So extreme events usually are optional for planning engineer to study. So if you just map them into different categories, so usually the planning engineer need to do some pre-screening on the extreme event to identify under some conditions, like extreme events may increase the probability to be almost the same level as N-2. Then they need to study those contingencies. Okay, but for the others, they're not happening very often. They can just ignore those ones. All right, so following this, we will go through a number of related terminologies. The first terminology is the operating quantities. So operating quantities means some physical quantities and which are useful for the operators to monitor the system and for planning engineer to know the condition of the system. Any such quantities will be considered operating quantities, such as real power, reactive power, and voltage and current in their RMS value, not in their waveform. The waveform is not very clear on what's happening on the system. You need to change the waveform, the 60 Hz waveform to the RMS value or phasor value. So basically here, the operating quantities are what variable we need to simulate or calculate by power flow and the simulation, dynamic simulation. You can easily match, compare the value each operating quantity to their threshold, okay, to know the security margin. Steady state operating condition. Steady state operating condition of power system means a condition all the operating quantities that categorize the system can be considered constant for the purpose of analysis. Even they are not constant, but they can consider constant. Okay. Like for instance, if the system has all bus voltages stay within 1% of their nominal value, so it's maybe fine to call the system is under a steady state condition. But if you look into the specific waveform, you see there are very little variation, but that doesn't raise any concern by operator, so they will be considered a steady state condition. Synchronous operation means each generator is operated in a synchronous way with the rest of the system. Or they are operating at the same electric speed. Electric speed is not the same as their actual physical mechanical speed, because different rotor have different number of poles, but they need to operate at the same electric speed. Electric speed to 60 Hz system is simply just it's simply just the 2 pi times 60, so which is about 377 radian per second. So the generator need to have the same electric speed. If we see a power system to be in synchronous operation, we mean all the synchronous machines are synchronized with the rest of the system. So they all operate closely at the same electric speed. Here is one example on what a synchronous operation may look like, right? So if you see all the machines, they have a changing frequency. Temporarily, some generator may be operating at faster speed, but they all stay very close to the 60 Hz. Then the largest variation is only 0.06 Hz. So it's very small, but you still can tell there's obvious oscillation, but we still can consider the system is in the synchronous operation, and finally the system reached the steady state condition. Next terminology is about the power system stability. Power system stability is the ability of a power system for a given initial operating condition to regain an acceptable state of operating equilibrium, either original or different after being subjected to a disturbance. So stability basically means if something happened and that something is a disturbance, it can change the system equilibrium, or it doesn't change the equilibrium, but it will cause the change of the system state. And after some time, a system can go back to the equilibrium safely. So that can be considered a stable power system. Although the stability of a power system need to consider everything about power system, which means if we see a power system to be stable, every variable need to be stable, right? If you measure every single variable, they need to maybe oscillate and finally reach to the value at equilibrium. But under some conditions, we understand the power system is very complex. And there's some variable that not go back to the equilibrium, but as long as it doesn't cause any big problem, we can ignore those one. So depending on what specific stability problem you're working on, and you can only select maybe a subset of stable variable, only make sure those variables to be stable. So later I'll give you some example. Like we have a root angle stability, voltage stability, frequency stability, like a resonance stability, like inverter-based stability, different stabilities considered as subcategories. So they all focus on a subset of stable variable. So considering an interconnected multi-machine power system as a whole, it's a conventional stability problem is mainly to maintain the synchronous operation of all synchronous machines. So if you're able to maintain the synchronous operation of all machines following any disturbance or following the studies, the given disturbance, system will be considered stable. You can only focus your study on a part of your system. And the part of system only consider how the generator within that portion can maintain the synchronous operation with the main system. Okay, this is very practical because in the US there's for instance, for the Eastern Connection, so that has a lot of power company, and each power company can only study the stability on their own, right? So they can use approximate or reduce model for the neighbors, but they focus only the stability issue on their region. So they don't have to simulate the entire system. And the motors, motor in some load, they can lose their stability. For instance, if the voltage is lower than a certain value, some air conditioner load, air conditioner will stop the motor, so which is called the stalling motor. That's only just to protect the motor of the air conditioner, but that doesn't cause too much impact to the system. So so you don't have to check every single motor of the system for stability. So we still focus on only the power plant, the generator in power plant, and also the network above 100 kV. Under 100 kV, below 100 kV, we can somehow simplify the system. We don't have to look into each individual motor of the system. Next terminology is the disturbance. Disturbance is a sudden change or a sequence of a change in one or more parameters or operating quantity of the power system. So basically it just means any parameters or the condition need to have at least a change, and no matter it's small or large. So there will be two types of disturbances. The first one is a small disturbance. The second, a large disturbance. A small disturbance means so for such disturbances, the system model can be linearized. And if you use a linearized model to do the study, that doesn't affect any accuracy of the study result. Okay, so using linearized model to study stability is good enough. Then such conditions can be considered small. So one example is the load change, right? So if the load only change a little bit, but the network topology is same, there's no loss of any line or transformer or generator, that contingency, that disturbance is considered small. So even typically when we use continuously this word, we mean large disturbance. But for small disturbance, that can be just like ambient change in the load. So that means what exactly happened on the system is not important at all. We only just assume there's a change on the system. The change can cause oscillation, but where exactly that disturbance, that change happened is not really important to us. The second type of disturbance is a large disturbance. So if the system model cannot be linearized, we have to use either nonlinear model, the detailed nonlinear model, or maybe somehow reduced nonlinear model. But we can keep the portion where the disturbance happened as accurate model. So that disturbance will be considered large disturbance. So the details of disturbance are important to accurate analysis, right? So for example, the type of disturbance, whether it's a line outage or the generator outage, even whether it's a permanent fault or like temporary fault. Permanent fault, which means if there's a short circuit and you have to isolate the element which has a short circuit away from the system. A temporary fault means it's maybe a tree just contacting the line and due to the wind, but after maybe a couple of seconds, the tree will leave. So that's temporary fault. But such details are very important to study. You also need to study the duration of the fault, or what happened following this fault. Just give you one example. So this is the swing equation to model a single generator connected to a large system, which is as known as the single machine Fehrenbach system. So the P delta is a nonlinear function. Later you'll know that's basically sine delta. It's a nonlinear function. For this system, we can study the disturbance of the system. But if we draw how the P can change with angle, the power can change with angle, that's a nonlinear function, part of a sine function. So if the disturbance only change the P and the delta very small around that equilibrium point, the equilibrium point will be the green dot. Okay, so the blue line is the tangent line at the green dot, which is the linear approximation of that curve, right? So if we for some contingency, it only just perturb the system away from the green dot, but still stay inside that blue square. You can tell the blue line and the purple line, they look very same. So even they have some error, that's not a big problem to your analysis. So you can use that blue line. You don't have to use this the purple curve, which means this disturbance will be small. But if the angle change a lot and to go maybe beyond that, the small square go to this rectangle. So you see there's a large difference between the blue line and the purple curve. And you do need to use the nonlinear function. So this will be the large disturbance. Okay, so to summarize small versus large, first of all, you need to have a model. And based on the model, you compare the result from original nonlinear model, the result from the linear model. If the result look exactly same to you, that disturbance is small. This is the only safe way to tell it's a small or large disturbance. Okay. You may don't just use like what I put on the left column in the wording. Like, okay, so load change will be small. Okay, line outage will be large. No. If the load change push your system go outside of that the blue square and make accuracy to be bad, you need to treat that one as large disturbance, just to use the nonlinear model. Even it's line outage, but they happen far away from your system, like a line outage in New England, far from Tennessee. Tennessee engineer definitely can treat that contingency as small disturbance. Yeah. Okay. Small, large really depend on whether you can linearize the model without affecting your accuracy of the result. So why do we need to do dynamic analysis? Because we need to know its performance subjected to any change, either small or large disturbance. So it's important if some change happens and is finished, the system can go back to some equilibrium. And through this entire process, there's no violation. Okay. So for instance, if we use this one example, after some disturbance, the generator will oscillate and finally will go back to closely at 60 Hertz. So by looking at this chart, you may tell the system is stable, right? But if you know exactly some criteria, maybe the frequency violation is during this period can temporarily violate some standard. Like if the frequency variation is not like 0.06 Hertz, it's 0.6 Hertz, that can make some of the unit to have a higher violation and it can be tripped by the protection. Okay, so if you only just calculate before the contingency and after contingency, that's not enough. You need to know the entire process, how the system transitions from the beginning to the end to make sure no variable violate their limit. Because if they do violate the limit, that will cause additional contingency, right? So there may be short circuit and some generator oscillate, and if you oscillate too much, that can trigger some out of step protection that can trip this generator. So that will become N-1 minus 1. Okay. When this generator trip and the rest of system, the frequency will go down. That can cause some voltage maybe lower at some value, then will trip some other like lines. That will cause N-1, -1, -1. So you can tell. So any cascading failures blackout can start from very initial, like single, double contingency. Right? So simulation will be very, very important. Oh, okay. So by doing the simulation or study the dynamic of the system following each contingency, we need to check to make sure that the new operating condition is acceptable. It doesn't violate any standard. Okay, based on static state analysis, and also system must survive the transition from the old condition to new condition. So that definitely need dynamic analysis. So one good example to show why dynamic analysis is important. This is a problem called FIDVR, or fault-induced delayed voltage recovery issue. So the curve describes what happened after a single fault, single short circuit fault. So you see at the time 0, and there's single short circuit fault, and that brings the voltage near the fault to be very low, close to 0. And after the fault is clear, and the voltage will recover. So it will go through a number of oscillations. Finally, will stay within an envelope. Will stay quickly within this envelope. Eventually, will stay even a narrow envelope. Okay. So this is just one standard from NERC about this event. So the standard says following each short circuit, the voltage dip should not exceed 25% at load buses or 30% at non-load buses. So if this bus is about a load, it has a lot of load. So this line is 20% of voltage. So if here is about 1, so here is 0.8. Okay. So if the voltage drop to 20%, so that time cannot be longer than 20 cycles. So this duration cannot be longer than 20 cycles. It can temporarily lower and this part is also lower. Definitely, if you have short circuit, that will be lower, but they need to be recovered quickly, and the duration should not be longer than 20 cycles. If it's longer than 20 cycles, that will trigger some protection. Okay, this one will become N-1 minus 1. And this one says after when the system go back to the equilibrium, go back to the steady state condition, the steady state voltage cannot be lower than 95%. So the violation should be less than 5%. So this one here should be 0.95. All right, so you see, even this one is not really about like a lot oscillation. So there's some buses you don't see a real oscillation. You only see the voltage slowly recover back and monotonically and go to the equilibrium. But if that recovering time is too long, that also violates standard. Okay, even the process doesn't seem to be very dynamic. You still need to do time domain simulation to check those dynamic performance. So that's why dynamic analysis is important. Even the system doesn't have any stability concern. It just try to avoid any further protection. Any question? We'll go back to this figure to talk about why this happened and how we can mitigate this issue in the voltage regulation, because this is part of a voltage regulation session.
You can post these notes on campus as well.
Oh, I forgot to. Yeah, I will do after this lecture. So now we have to clarify the differences between three terms. The first one is secure, second is stable, the third is oscillatory. So what are the differences between those three? Yeah, so if you talk to some like engineer or some like student scholars, usually the usage of those terms are not very accurate. They can misuse those terms. In order to differentiate those three, we have to first give the definition for each, and also we try to identify some example which fall into the one but not the other two. Okay, then we can check the boundary. Secure means they meet all the NERSC standard. That's just simple. Okay, so NERSC says if you operate system, all the standards need to be satisfied. If you satisfy all of them, that you are secure. But keep in mind, the standard can change, right? Today, your system is secure. Doesn't mean when the new standard come out, your system is still secure. It can be insecure. So you need to do such study regularly, right, based on the newest standard. If you violate any standard, that's called insecure. Stability is simple. Stability we already defined. It just says after disturbance, the system will transition to a equilibrium. The equilibrium can be a new or old. It doesn't matter if it's a temporary fault, it will be the same equilibrium. If it's a permanent fault, if you lose a line, lose a generator, the equilibrium will be different from original. But as long as it can get to that equilibrium safely, not safely, can get to there, eventually the system will be stable. If it cannot reach that equilibrium, it will be unstable. That's purely from the dynamic system perspective. Oscillatory means there's some variable will go up and down. There's some periodic behavior of which can be visualized from some variables. Okay, so that sounds the three terminology are very close to each other, but they do have some differences. Yeah, the secure means no violation. All right. Stable means it can get to the equilibrium. It can be new, it can be old. Oscillatory means it's just a periodical change. They have certain frequency of such periodic behaviors. But if I have to give some example, some power system can be stable, which means if you do the simulation, it will go to the new equilibrium. But if you check all the operating quantity, you find out some quantity violate their standard, which means this system is stable but not secure. Because stable is a broader concept, right? It's from the dynamic system perspective, but secure is really based on the regulatory issues, like how the people regulate the system and what do you expect for the system to operate. Like for instance, if after disturbance and system go back to 60 Hertz, but during this period and some generator, the frequency drop to maybe 50 Hertz or 55 Hertz, very low temporarily, but that can damage the generator. Okay, based on your simulation, you tell the system is stable, but if you implement the control to the real system, some generator will be damaged. So that should be avoided from the standard. So that's not secure to that generator. So there's some oscillations. If the oscillation have a decaying amplitude, and which means the system is stable. But if you have a growing oscillation, the system will be unstable. It can also become insecure. Okay. So if we put this this bubble about stable system, secure should be smaller. Okay, a secure system has to be stable because the people who develop that standard are not idiot. They have to treat everything they require to be secure had to be stable, right? So secure should be much smaller and stable system. And oscillatory is different. Oscillatory can be stable or unstable, can be secure or insecure. And there are some stable systems or secure systems they don't oscillate at all, or they don't have obvious oscillation. One typical stability problem is called voltage stability. It doesn't need to oscillate. So you have many scenarios, they don't oscillate. They will just, you see the voltage keep declining until system collapse. So even for power system, there's no synchronous generator, they still have voltage stability problem. Okay, so that is good example on the stable, unstable system, but there's no oscillation. Any question? All right, so now we have to show this this chart about all the states of a power system in operations. So we start from the green bubble on normal, which indicate all the normal condition. All normal condition, which means they meet all the NERSC standards, all security, all reliability security standards. Also, they need to be able to withstand any single contingency. Okay, so for any system condition falling in this bubble, it has to meet all standards. And if you take a single element off and recheck all standards, it's still satisfied, which means it has enough margin to withstand any single contingency. That's called normal. Okay, that typically we call it normal. It's a P0. So if we regularly check contingency and we know that for single contingency, the system may become insecure. But this contingency has not happened yet. But if it happened, it will cause violation. Then that become alert state. So I need to send alert. I tell, okay, that contingency will cause violation, even it's not happened yet, but you need to be careful. And for the operator, they can check if that contingency will never happen under maybe today for this condition, that may not be a big concern. But if it does have some chances to happen, then you need to do something to make that contingency to be secure again. Then you can go back to normal condition. So that control is called the preventive control. So preventive control is for alert state, which means both normal and alert are safe. Okay, they're both safe. Then they don't violate any standard, but preventive control just to increase the margin to make it even safer. Okay, more reliable. So we can consider the both as somehow like safe states, but this is normal, that's alert. Okay, but if it fail, if we cannot go back to normal, the system may go to another condition, which means there's some contingency can cause violation, and one of such contingency already happened. They really happen. Okay, now the system is not safe anymore. Okay, so this condition is called emergency. Emergency means it's insecure. Some standard has been violated, but violating standard may not be the end of the world, right? Because like if you set up the standard like 95% of the voltage, but now become 94.5, right? A little bit lower. It doesn't cause any damage. It haven't triggered any protection yet, but you still need to take action as soon as possible, right? Because if the voltage further reduced, and it may trigger other event. But so far, the system is still stable. It still can operate. But you do see such a violation. Then you need to do control. Such control is called corrective control. So you can do very strong control to bring system back by one step to the normal condition, or you can just maybe just eliminate this violation to bring it back to alert state, but still without enough margin. That's fine. But such control is called the corrective control. So if you also fail, okay, and there could be something happen to go to the extreme state, that cascading failure, that's fully out of your control. Another possibility is you can sacrifice some of your system. So if the security problem only happen within one local area, I can isolate that area as an island, and the rest of the system is safe. So that will go to a new state, because this state has violated integrity. Remember, we mentioned number of things. Integrity is important. This state, and that state, they all have the integrity of the entire grid. The entire grid hasn't been broken yet, but this is like not the original topology. You may have lost some islands, so it's okay by taking the emergency control. You go to that restorative state, and then you can bring the system back by restoration. Or you can just let cascading failure happen until it stops, which is like blackout, and then you bring system back. Why I need to emphasize this chart, because if you want to write paper report, and you have many chances to talk about like what condition, emergency condition, extreme condition, normal condition, and what control. Try to follow this chart, okay? Don't define your name, because I do see some research paper, they say, okay, after single contingency, I need to do emergency control. But that's defined by you, but I'm talking about, this is like consensus by the power industry. Okay. This is closest to what power industry are looking at system, and that can make your communication much easier. So, for instance, if you present my paper can do emergency control, then the industry people will understand you are talking about system which is not secure anymore. Okay, then you can do islanding, you can do load shedding. That's fine, because your system is not secure, and reliability become the #1 priority. So even you break the system into island, that you can do that if you can save my system. But if you say after single contingency I need to do islanding, nobody will agree with you, right? You need to do preventive control. Okay.
Why
Yeah.
does the restorative state feed back into the emergency state?
Yeah, you fail. If that's what I mentioned in the drill, right? To fail a number of times, and they'll go back to emergency. Emergency means violation, but restorative means no violation. But the system doesn't have integrity. It's part of system, or maybe separate islands. But for each island, the system in each island is similar to alert, which means it need to meet some standard. But maybe NERC has some static standard talking about the restorative state. Temporarily it's okay. Like this is just my reasonable guess. Like for voltage, we expect to be higher than 95%. But if the system is in restoration, maybe 94, 93 is also okay. Okay. Yeah.
An emergency, what determines whether you take corrective to alert or emergency to restorative?
Yeah, that's up to you. That's also up to you. If you can design very strong control, but that depends on how strong this control is. So this chart is just try to let you know the consensus of terminology. It doesn't help you to select which type of control to use. As engineer, you need to pick whichever is best to your system. Don't worry about whether you call it preventive, corrective. But when you communicate, because doing research and solving real problems are very different. If you're an engineer working with power company, okay, they say, okay, last month we have power blackout and there's some violation, system break into islands. Can you propose any solution? You just collect the model data and do the similar study to see when the oscillation happened, when the violation happened, and just do some control. Even you just maybe reduce maybe 5% the load, or open this line or bring this back. That solves the problem. Okay, then when you don't have to have this chart in your mind. You just solve the problem. And when you implement this problem, you can call it like a corrective control if it really start from a system which is not secure. Okay. If the system is still not too bad, you can call it a preventive control. This is just for you to easily communicate with other engineer about what you just did. But if you are a researcher usually you just start from initial condition assumption of system and try to propose some control method. And once you propose a method, you want to sell the idea to engineer, you need to pay attention to this chart, right? Don't sell the idea to wrong people, to be the right group of people. They really care because maybe your method you need to sell to some engineer, they deal with the extreme condition, not deal with the alert condition, because they may belong to different sub teams of the company. Okay. Because I do see a lot of misusage of those terminology in some research paper. If you ask me who draw the chart, the answer is I draw the chart. But based on my understanding, right, this can minimize the miscommunication with power industry. Okay. But maybe later this one can be changed. I mean, the future have a lot of IBR, but this so far is still safe. This chart. Quinter's book should have maybe a subtitle talking about this transition, but I just visualized this one in this slide. Okay, what else I need to emphasize? Yeah, that's pretty much what it is. Okay, so in the next section, we're going to talk about the modeling. So we'll start from generator modeling, and the section number 2 will only focus on generator modeling. We start from the ceiling pole rotor generator, round rotor generator, and we develop the equivalent circuit for all the windings, the rotor winding, stator winding, and we try that those circuits for simulation, and we gradually simplify the circuit and equation to swing equation. So you'll be able to go through the entire journey from very detailed model to very simplified model. Okay, because I don't want to directly go to some simplified model. So that's it. So just use that model for research. You really need to understand what has been simplified. Because some dynamic, if it's simplified, it cannot show up in your simulation result. Okay, you need to be smart to decide which can be simplified, which cannot. Like one example is if you use oversimplified generator model, okay, then you do some like electromagnetic transient simulation. Like you connect the generator to a system with another wind farm or solar farm. So solar farm, wind farm use a very detailed model, but your generator use oversimplified model. That doesn't make any sense. You need to use a model at about the same level of accuracy. So that's generator modeling. And we also talk about the load modeling. Load modeling just represents the aggregated load presented to the system. And in the following section on the voltage regulation, we'll talk about the modeling of the excitation system and other voltage controllers. And in the frequency regulation, we'll talk about the governor and turbine model and also frequency regulation, which is automatic generation control. And then we'll go to the stability of the system. Okay, so yeah, that's pretty much what we have today. So let's continue on next Tuesday.